Yeah, welcome everyone. So I'm very happy to introduce Martin Schmidt today. He's a full professor for nonlinear optimization at Trier University. And yeah, he's well known for his works in bilevel optimization and also gas network optimization. And he won several prizes already for best papers in optimization letters or European Journal of Computational Optimization and many more. And who follows him on Twitter also knows he's very influential in non-academia stuff like baking bread or brewing beer. So very happy to hear your talk today. Please go ahead.
Yeah, thank you, Yannis, and also the other organizers for giving me the opportunity to talk today here. So let me first share my screen. You should see it now on full screen. And you should see my mouse cursor, right? Okay,
yes.
Perfect. Good. Yeah, as Yannis already said, my main research interest is on bilevel optimization. But actually, robust optimization and bilevel optimization are not so different when it comes to their mathematical structure. And this talk is mainly about the connections between these two fields. So this is the team which did all the work. So if I come to that point, I'm not sure when I will be stopped by Yannis, but if I come to that point, I will talk a bit also about robust techniques in bilevel optimization, which is kind of the second part of the talk. And this is joint work with Jasmin Beck and Ivana Lupic. And the first part of the talk, which is actually about the connections of bilevel optimization and robust optimization, is joint work with Mark, with Yannis, and with Johannes. Yeah. Okay, so I mean, I already sketched this a bit. It's a bit split into two parts. So the first part is really about the connections of robust and bilevel optimization. And if I come to that point, the second part is about bilevel optimization under uncertainty. So it's not about the connections anymore, but about problems and how to solve them if you have robustness in a bilevel optimization model. Okay. So before I really start with the content, whenever there is something weird or bizarre that I'm saying, or if something's not understandable, just interrupt me and ask the question. Maybe, I mean, I cannot look into the chat all the time, but maybe Yannis can have an eye on that, and then you can just directly ask, okay? Good. So let me start with the connections between these two fields, and let me mainly start with the motivation why we did this work. And I would say this mainly started with a workshop in Dachstuhl that we had last year, which had the title Optimization at the Second Level. And this workshop was actually about bringing together people from robust optimization and bilevel optimization to discuss the commonalities and maybe also the difficulties and different things in these two areas of bilevel optimization and of robust optimization. And there was a survey. So this is not, I hope it's not top secret, but it was anonymized anyway. So I have no clue whom I am citing here. But so one of the questions, of course, in this survey after this seminar was, what are the best and the worst aspects of the seminar? And there was one, I mean, the favorite or my favorite answer there. So it was like a bit of a twofold answer. The first one, the best one, was that it was a very active audience, so everybody enjoyed the workshop a lot. And the second part of the reply was that the worst of the workshop was that this participant, I have no idea, of course, who it was, found out that robust optimization is just a special case of bilevel optimization. Okay, so I have no idea who was it, but later on Twitter, the organizer of this workshop started to publish results based on some ChatGPT research. So here's a post by Yannis. So he was not yet really sure, maybe, and he asked ChatGPT, and he was, I guess, relieved by the answer that ChatGPT said, well, no, robust optimization is, of course, not a special case. But there was a thread that then started. So Ryan Corey Wright from the MIT at that time asked two different things. I will talk you through these things in the next slides. And I mean, the conclusion in the end by Yannis was that ChatGPT kind of prove that P is NP with these answers. So what was the question by Ryan? So first he asked, why is bilevel optimization a special case of robust optimization? So the answer was positive, and there was a reason that was given, but I mean, we don't have to go to it. But he also asked why robust optimization is a special case of bilevel optimization, which according to ChatGPT also is the case. I mean, this is mainly the P is equal to NP proof then, if you apply this at least to the right instances or models here. So it was a bit contradictory. So after this workshop, Mark, Jannis, and Johannes, we teamed up and we wanted to find out. So what is actually the relation between robust optimization and bilevel optimization? And the results, I would say, they are not super mathematically deep, but at least to the best of our knowledge, it was the first time that this was kind of formally written down. And I'm going to talk about the results here. So before I talk about the relations, I have to introduce the problem classes. So here is what we call an optimistic bilevel optimization problem. So we have a so-called upper level problem. So everything that is in capital letters here, the objective function f and the constraints g, they belong to the upper level of the bilevel optimization problem. And we have two set of variables, x and y. We call x the upper level variables, y the lower level variables. And the bilevel-ish constraint here is that in bilevel optimization, you ask for that a part of the variables here, y, of the optimization problem is the solution of another optimization problem, which is this x parameterized. So it's parameterized by the leader's decision. The leader is the guy who is controlling the variables in the upper level. And this y variable, the followers variable, have to solve this optimization problem. So this is why it's called bilevel, right? There is a very important detail here, namely that the y variable also appears below the min of the upper level here, which indicates what we call in bilevel optimization the so-called optimistic version of the problem, which means that whenever we have a problem here in the lower level, so that the y is not uniquely determined, since there are multiple solutions, the optimistic version of the bilevel optimization problem is the variant in which the leader can choose among the optimal y's so that it is in favor of his or her objective function in the upper level. That's why it's called optimistic. There is also the pessimistic variant, which in this variant, how I put it here, dates back to a famous paper in SciHop by Wiesemann and co-authors. So it's exactly the same except for two things. So first of all, you do not have the minimum over x and y here with respect to the upper level objective function. But this is now the pessimistic setting. So whenever there is a multiplicity in the solution set of the lower level problem, the follower kind of chooses the y that is the worst case y in terms of the upper level objective function, which leads to this min x max y structure. Yeah. Okay. And if you even have the case that the constraints here in the upper level also depends on the lower level decisions, the pessimistic case is the one in which you have to ensure with your choice of x in the upper level that for all possible solutions of the lower level, the upper level stays feasible. And here you directly see, I mean, even on just on a syntactic level, that this is already pretty related to robust optimization, because this looks like a classic robust constraint here. Okay. The lower level, by the way, is exactly the same. We don't have any differences there. Okay. So this, everybody in this seminar series, I guess, knows what it is. This is the classic static, or I will call it strictly robust optimization problem. So we have an objective function. We have some constraints that are certain. So there's no uncertainty affecting these constraints. And we have some constraints that are also parameterized here by the uncertainty u. And then, as you know, we have to choose the x so that for all u in the uncertainty set, we keep feasibility. And for the ease of presentation, all the uncertainty here is in the constraints. So without loss of generality, at least in this case, we have a certain objective function. Okay. One important special or case or generalization, better to say, for what follows is the case in which you have decision-dependent uncertainty. That is the case in which this uncertainty set here depends, as it is denoted here, on the upper level, no, on the decision x. Okay, so this is strict robustness with decision-dependent uncertainty sets. And we make the standard assumptions. So for every feasible point, the constraints that are affected by uncertainty, they are continuous in the uncertainty, and the uncertainty set should be non-empty and compact so that we have kind of a well-posed problem. Okay, so what was our main research question? The main research question that we wanted to answer is given here. So assume you have two problem classes, calligraphic P and calligraphic Q. And let's assume you have an instance of a problem in P, and you have an algorithm for solving problems in Q. Question, can you then also use the algorithm to use the problem P? In other words, this is something like, is P a special case of Q? Or does P contain special cases of instances in Q? To make this a bit more concrete, when applied to bilevel optimization and robust optimization, what we found out, I will give you the theorem later, or in a minute already, is that one can use an algorithm that is intended to solve optimistic bilevel problems to solve strictly robust optimization problems. So whenever you have a strictly robust optimization problem, you can rewrite it as a bilevel optimization problem so that you can apply your standard solvers there. So this was the key idea that we wanted to study. Can we use algorithms, let's say from bilevel optimization, to solve robust optimization problems, and maybe the other way around, depending on the relations that we will find out. Is that clear? Any questions so far? This means in particular that we did not study these things from a complexity point of view. It's not that we discussed the relation between different problem classes here from the point of view of complexity theory. I will slightly come back to this point later on when we have kind of negative results when it comes to reformulations, but we only sketched this. It was not our main purpose here. Good. So here's the first main theorem, and it mainly tells you that a bilevel optimization code can solve decision-dependent robust problems. So how? So again, these standard assumptions, I'm not repeating them here. These are technical details. They are satisfied, and assume that you write down an optimization problem that looks as follows. I already use here in the statement of the bilevel optimization problem the notation from the robust problem that I introduced before. So the upper level objective function is just the objective function of the robust problem. And I have both the uncertain and the certain constraints here in the upper level. And I just move the uncertainty or the decision about the realization of the uncertainty in the lower level problem. So the player in the lower level problem kind of is the uncertainty player now. So it means that this U here, or UI, U is just the vector of all the UI. This is the solution of the lower level problem. And in the lower level problem, we now maximize the sum of all these constraint values, which kind of gives you the robustness, because if you maximize them here with respect to U in the lower level problem, then if this is feasible, you know that you are strictly robust feasible, okay, just by construction of the problem. So the lower level just optimizes the constraint values here, maximized because we have smaller than or equal to constraints. And the feasible set in the lower level is just this decision-dependent uncertainty set here. And since everything is kind of separable, we can just take the sum here. This amounts to just maximizing every constraint independently, because we have this independence assumptions as you usually pose it in robust optimization when it comes to the uncertainty parameterization of the constraints. Well, and if you solve this bilevel optimization problem, the solution X star that you get out of it, so the upper level solution, is a solution of the strictly robust optimization problem with decision-dependent uncertainty sets. Okay. So this means kind of that what Janus wanted to find out while asking ChatGPT if robust optimization is a special case. This result tells you, yes, it seems to be the case. But I mean, there's also another direction. I will come to this on the next slide. But first, here's some remarks. So, I mean, let me go back. Here I have the decision-dependent uncertainty. Of course, I can do this without the X dependence as well. Okay, so this works for the classic setting where the uncertainty set is not depending on the decision X itself as well, of course. And the nice thing kind of is that the assumptions that you usually pose in robust optimization to get kind of a tractable problem, so concavity of the constraints with respect to the uncertainty, and kind of that you have interior points in the uncertainty set, which is kind of a Slater constraint qualification, really exactly translates to the nice assumptions that we pose in bilevel optimization in order to get a, tractable or practical bilevel optimization problem. Not tractable in the sense of being in P, but you can do something. Okay, you can reformulate as a single level optimization problem, you can dualize, etc. If you try to do this even with pessimistic bilevel optimization problems instead of optimistic ones, it turns out of course that this is possible as well. You do not even need a lower level objective function. So here we just put a 42. So every feasible point is optimal with respect to the follower's problem. And just due to the pessimistic nature, the lower level solution will be chosen to be the one that tries to violate, for instance, feasibility in the upper level as much as possible. So you directly get this setup from the pessimistic point of view without any need for an optimization or for an objective function in the lower level. Okay, so the other way around. So the question is, can I also use, let's say, a solver for strictly robust decision-dependent uncertainty set problems to solve optimistic bilevel optimization problems? And that's the case as well. So here is the strictly robust problem. You take the upper level objective function, you take the upper level and the lower level constraints, and with this kind of robust way of writing it down, you model the optimality of the lower level decision. So you say the lower level objective function for the variables x and y that you choose in the end should be smaller than, for the given x, the value that you get if you vary over all y tilde here, and y tilde just varies over the feasible set of the lower level problem. By this, you model optimality of your y decision. Well, this is nothing but a decision-dependent uncertainty set. So if you solve this robust optimization problem here with x and y as the outcome of it, you get a solution of the optimistic bilevel optimization problem. But here it's important that you have a decision-dependent uncertainty set. Because here, if the lower level constraints of the bilevel problem actually depend on x, which is usually the case, then you need this decision dependency. But these two theorems tell you that these problems are kind of equivalent in the sense of that you can solve it with algorithm A. If it solves this problem, then you can solve also the other problem, and the other way around. So this is the takeaway, the first take-home message here. Okay. In this sense, optimistic bilevel optimization and strictly robust optimization with decision-dependent uncertainty sets, they are equivalent in this sense. Okay. Well, by the way, this is all equivalent to what is called generalized semi-infinite optimization. And this is rather interesting, at least it was for me when we found this out on, let's say, a formal level, because it means that if you go to the literature of the last, let's say, 20, 30 years, it seems to be the case that there are three different streams of literature: the bilevel literature, the robust literature, and the semi-infinite literature, which is more or less disjoint. I would say more than less disjoint. But they actually deal exactly with the same problem. It's mathematically all the same. Okay. So this is, I mean, one of the motivations why I give this talk here. I will mention this later on again a bit more in detail, but I think we should open the eyes here a bit more in order to really see what from the other field can we use in our field. Okay, and this can be seen from, of course, all fields' point of view. There is a question in the chat, I see.
Oh, it was just a compliment for the objective function.
Yes, thanks. It was a pleasure. Good. So, of course, the question turns out now, what about the pessimistic case? Can I also write down the pessimistic bilevel optimization problem as something that is robust? And the answer here is yes, no. I mean, formally, you can write down this problem, which is a problem that formally looks like a robust optimization problem with decision-dependent uncertainty sets. I'm not going into the details here. The mechanism is kind of the same as before. It's a bit more complicated. The crucial point here is that if you want to do this with the pessimistic bilevel setting, you have to use in the definition, at least we had to use, in the definition of these decision-dependent uncertainty sets here, this function chi. And this function chi is the optimal value function of the lower level problem of the given bilevel optimization problem. And this is a bit dangerous to do. I mean, if this lower level optimization problem is something that is, let's say, convex and you have a proper constraint qualification, you can dualize, and then you can actually write this constraint here with the optimal value function down. It's getting larger, but only polynomially sized larger. So this is fine. This is what we do in robust optimization if we apply the classic duality trick, or it's more or less the same. It's the same idea behind. But if, for instance, this is not possible, if you don't have a duality theorem for the lower level that you can apply, let's say you have a general mixed integer linear program, okay, an NP-hard problem, then just writing down this optimal value function here and just pretending as if we can work with it as a usual constraint that we can just evaluate means that, well, kind of the polynomial hierarchy collapses, okay? So then we assume that we can just evaluate this function behind as an NP-hard problem, and by this sigma 2p-hard problem reduces to something that is easy, okay? So this result here does not mean that it is impossible to write down a pessimistic bilevel problem as a robust problem. But as we did it here, we actually think that we need to use these optimal value functions in the formulation of the uncertainty set. So in order to have, let's say, a negative result here, I mentioned this briefly before, we think, or I think, that you have to go to complexity theory and prove this in a complexity theoretical sense that this is something different, okay? And the key idea, at least in my brain, would be that here the evaluation of something that is maybe in NP cannot be easy. Otherwise, the hierarchy collapses. Good. So, of course, the question on whether robust optimization and bilevel optimization is the same, or one is the special case of the other one, depends on the specific bilevel problem or the specific robust problem. So this was strict robustness. Let's go to two-stage robustness or adjustable robustness, which is also very popular, of course. So the problem you all know, you minimize over your first stage decisions, then the U here, the uncertainty realizes, and then you have your second stage decisions. And the feasible set here depends on your first stage decisions, X, and on your uncertainty realization, U. Okay, so this is X is here now, Y is wait and see, you all know this. And this lower level, or no, not lower level yet, but the second stage constraints here depend on everything, or they may depend on everything. So the question is there a counterpart in bilevel optimization where this is again the same? And yes. There is a counterpart, and this is a so-called robust bilevel problem with a wait and see follower. So also in bilevel optimization, you can introduce robustness, and then since you have two decision makers that act at different points in time, you have to decide in your modeling when does uncertainty realize. So bilevel with wait and see follower means that first you, as the leader, decide. Then your uncertainty realizes, and then the follower is able to decide upon his or her Y variable. And this is then the solution of the lower level, which is again parameterized here by U. So from the point of view of the follower, uncertainty is a given parameter. Okay, so this is why it's wait and see. And you again see here this kind of min-max-min structure, which already looks pretty similar to what you have in two-stage robust optimization. So the theorem is as follows. So whenever you have a solution X to this robust bilevel problem here with a wait and see follower, where you have the objective function in the upper level, which is just the objective function of the robust problem. The uncertainty is just the uncertainty set of the robust problem. And in the lower level, you kind of have the same objective function and the second stage constraints here. Then a solution X star of this bilevel problem is a solution of the two-stage robust problem. Okay. Michael, you have a question?
I do. Sorry, I don't understand. You have twice the same minimization of H.
Yes.
I don't get it. I don't get it. I don't see why it's useful.
I mean, if you want to rewrite the two-stage robust problem as a bilevel problem, which we actually do when we prove this theorem, we have to state two objective functions, one of the leader and one of the follower. However, and the reason is because in bilevel optimization, we have two players that are actually different players, the leader and the follower. In two-stage robust optimization, you have the same decision maker.
Let me rephrase my question, if I may. If you replace S of XU by just H, X, Y, U less than 0, don't you get the same problem?
Yes, but then it's not formally the bilevel problem that I posed before. Yes.
Okay, thank you.
I think you're right, but in order to show really the relations, you had to rewrite it in this form so that we actually see how are the relations between the robust world and the bilevel world.
Okay, thank you.
But my way of viewing this is that you actually here see that the difference that in the one problem class you have one decision maker and in the other one you have two. There is another question by Shabnam.
Thank you so much for the presentation. I have a question about three-level interdiction model. Because with two-stage robust optimization with budgeted uncertainty, they both have the min-max-min framework.
Yes.
But I don't understand what are the differences between these two. I know that like in interdiction, we say that there are two players, and in robust optimization, as you mentioned, it's only one player, but the mathematical models are the same. But I don't know why some papers go by robust literature and some papers mention that it's interdiction. The differences are not clear for me.
I think if you really stay with this interdiction problem, there is no difference. And this is actually one of the points that I want to make today, that there are different parts of the literature in robust optimization and in bilevel optimization who are actually trying to tackle the same problems. And the people, I mean, saying it in a harsh way, do not talk to each other enough. Yes. I mean, so, I don't see your problem formally right now in front of me. So we would have to discuss, of course, the details here. But if you go to interdiction kind of things and or to these tri-level problems, I think that in very many of these cases, it's actually the same as the two-stage robust setting. Yes. Depending on how you write down the uncertainty set, if they have an interdiction-like coupling in the lower level, like in this capital H, if this is an interdiction-like constraint where U is interdicting the use of something so that Y cannot be properly used, this is exactly the same.
Thank you.
Maybe a short comment there, but the difference is still that in a bilevel setting, the follower can have a different objective function, right?
Can, but does not have to. If you are in this interdiction setting, and if you really have the min-max structure, then it's very much the same.
Yeah, but maybe that's important for the question because like in the special case here is that the leader and the follower objective is the same.
Yeah. Yes, exactly. Yeah. Okay, good. Thanks for the questions. The other way around here is kind of possible, but again, in quotation marks, requires optimal value function. So I think that there is a negative result, but in order to make this formula, I guess you have to go to complexity theoretical reasons. Okay, so last relation here is the one between min-max regret optimization and bilevel optimization. And I will just briefly sketch this, because here you can again see that there are some relations. So this is one of the classical ways on how to write down a min-max regret problem. So what do? You choose your decision X before the uncertainty U realizes. You do this in order to minimize here the capital X, which depends, the capital H, sorry, that depends on the uncertainty. And you try to find, no, that was not really correct. You try to decide upon your X so that you minimize the maximum regret. Now, this is why the problem has its name. And what is the regret? The regret here is the difference of the objective function value that you get if you choose your X before you know the uncertainty, and the one that you get if you can wait for the realization of the uncertainty and then choose the best Y fitting to this. This is the regret, okay? The difference between the decision that you make without knowing U and the decision that you make with knowing U. And you minimize the X so that the max regret is minimized, okay? And the constraints here just depend on X and U. And again, I will not go into the details here. This looks technical. It is a bit technical. It's not complicated, but I mean, it's just notation that we used or that we needed to write this down formally. So the take-home message is that if you have a pessimistic bilevel optimization problem and a solver, let's say for this, you can solve this problem, and by this you solve the min-max regret problem. But in this very general case, and this means that also the uncertainty here is part of the constraints, you need a pessimistic bilevel problem. However, a lot of the literature in min-max regret optimization considers the special case in which only the objective function is affected by uncertainty and the constraints are actually certain. So here are some important papers in this direction. If you have this special case, you can solve an optimistic bilevel problem in order to solve the regret problem, but only if you don't have uncertainty in the constraints. Okay. So again, I'm not going into the details of the reformulation. The main ideas are the same on how you reformulate it, but the more complicated the robust problems get, the bit more technical the reformulations get. Okay, so what do we know now? Well, this is kind of the overview of the results. So we know that a strictly robust optimization problem can be modeled or rewritten as an optimistic bilevel problem. So the arrows can be read here as can be written as, if you want so, or can be solved by a solver for. If the decision dependence is part of the problem, then these two problem classes are actually equivalent in the sense as I discussed it before. You can write this down, of course, as a pessimistic optimization problem. The regret problem can be written as a pessimistic or an optimistic bilevel problem. It depends on where the uncertainty is, or if the uncertainty also affects the constraints. And the two-stage robust optimization problem is solvable by solvers for, let's say, robust bilevel optimization problems where we have a wait-and-see follower. Again, here, the other way around would be in principle possible, but then you have to optimize over optimal value functions, which might lead to tough problems. Okay, so what's the use of it all? I mean, why do I talk about this? I mentioned this already at the beginning. I mean, first of all, we just wanted to know. I mean, there was this kind of vague discussion and we just wanted to find out, okay, what is actually the truth now? And here are our results. And I think the main, outcome of this work is that I really think that these different communities, let's say, robust or bilevel optimization, actually should talk much more to each other. Because, in the worst case, there are very many methods that are just rediscovered here or there. This kind of symmetry of ignorance, let's call it in this way, can go into both directions, of course. But to put it a bit more positive, it just might be the case that in field, let's say A, we already have a method that can be used in field B to solve a problem for which there are not many solution approaches right now. So one idea here would be, for instance, to consider this kind of equivalence between the decision-dependent, strictly robust problems and the bilevel problems. So we have a lot of algorithms for bilevel optimization. as far as I know, so I'm a bit ignorant, or at least I'm more ignorant with respect to robust literature than to bilevel literature. So at least to the best of my knowledge, there's not much for decision-dependent uncertainty. So maybe you can just exchange these ideas. So we started a bit with this. So if you're interested, just contact these two postdocs here in Trier, and then we can join forces. So we already started to try to make this work somehow. Yeah. Good. That's what I wanted to say about these connections between these two fields. Are there any comments, shitstorms, questions regarding this part? Michael.
Yeah, so my partial knowledge on this is that really decision dependent, there is not much if the decision variables are not binary. So what I understand from your talk, the first takeaway would be really to use the bilevel algorithm to solve this problem.
Yes, this is exactly. This is what we are right now trying to do. Just, I mean, very simple idea, right? I mean, write down this decision-dependent uncertainty set problem from robust optimization as this bilevel optimization problem from the theorem and throw it into a solver. Let's see what it gets. And then, of course, I mean, you have kind of a special structure. You can still try to tailor down the general purpose bilevel methods that are out there in order to use or to exploit the special structure that your robust problem has. Okay, this is still possible. So this would be the add-on then. But yes, exactly, this is what I'm talking about. Does this answer your question?
Sure, thank you.
Okay.
I mean, I would be curious about what you can do to tailor down, but that's not the place to discuss that. So we keep that for next time.
And if you would ask, my answer would be, I don't know yet. I mean, we didn't do it yet. Okay, so in this, how much time do I have left?
I think you can go for 10, 12 minutes.
Yeah, okay, that's fine. So let me talk a bit about another connection between bilevel optimization and robust optimization. And this is something that introduces gamma robust followers in bilevel optimization under uncertainty. And this is what mainly Yasmin did together with Ivana and me in the past. So here's the problem. That's the nominal problem, okay? It's a bilevel problem, it's mixed integer. Everything is linear, so this is nice. You have here in the upper level constraint, a mixed integer linear set. And the lower level problem is just a binary problem. I will let you know afterward where we need this. And we have the classic assumptions, because I don't know if the time is enough for this entire part. I will skip the details here a bit. These assumptions are just the classic assumptions in mixed integer bilevel optimization to ensure existence of solutions mainly, okay? So something like non-emptiness, compactness, blah, blah, blah of the required sets. Okay. Good. So how do we deal with this in bilevel optimization? Usually, well, we write down the problem as a single level reformulation, as you see it here. We copy the upper level objective function. We copy all the constraints from the upper level and the lower level. And we write down what is called the so-called optimal value function constraint. So phi here is nothing but the optimal value function defined here of the lower level problem. And if you ask for, if this is a maximization problem, that the lower level objective function is larger than or equal to this optimal value function, in the end, this will be satisfied with equality and guarantees that you're optimal in the lower level problem. So this is equivalent. I mean, this is old stuff. Usually in bilevel optimization, we always assume that these coefficients here in the lower level objective function are known, and now we consider them to be uncertain, and we follow a gamma robust approach a la Bertsimas and Sim. Okay, so what do we do? We replace the single level reformulation here with this one, where you have another lower level solution set. We call it now as gamma. I'm going to the question in a second. I just say what the problem here is. And this as gamma of x is just the solution set of the x parameterized and now gamma robust lower level. And what is gamma robust? Well, you maximize over your over your objective function. And then, as I said, a la Bertsimas Sim, you take the maximum that you subtract here over the all possible subsets of cardinality gamma so that you get the worst case outcome of the objective function. This is the gamma robust follower. So let me see what's in the chat. There, maybe I can postpone this question to the very end, to the questions and answers at the very end, okay? That because it's not related to where I'm right now. Okay, good. So then, of course, I again have an optimal value function. It's just the optimal value function now of this lower level problem here. So I just copy the terms, nothing happens. And then the single level reformulation is exactly the same. I just have the new optimal value function here. And this is my extended objective function when I follow the gamma robust approach in the lower level. Okay. So this looks a bit complicated because there's a bit of notation, but it's not. Okay. It's just you do the gamma robust stuff that you know from robust optimization for the follower. Okay, this is again the problem, and we make the same assumptions as you usually do and as Bertsimas and Sim did. So all these deviations, they are non-negative and they are ordered in some way so that you have that the uncertainties get smaller with increasing indices. This is without loss of generality, and this is just a technicality that Bertsimas and Sim needed to use in their proofs, and we do the same in ours. Good. So what is the key result by Bertsimas and Sim? And the idea was to bring this to bilevel optimization. So the key idea or the key result by Bertsimas and Sim was, I'm not going to the detail, I just tell you the story. If you have this gamma robust optimization problem, you can solve it by solving a finite number of problems of the nominal type with modified objective functions. But if you have a solver for your nominal problem, you can apply it a few times, then you take the maximum of all the outcomes that you get and prove, shown by Bertsimas and Sim, this gives you the gamma robust solution. So we can do this now for the lower level problem. So we say our lower level optimal value function is, according to Bertsimas and Sim, nothing but the maximum. They use these n+1 many problems, so dimension +1 many problems that you have to solve. And phi L of x now is the optimal value function of this lower level optimization problem with a modified objective function coefficient. This is nothing but the standard Bertsimas-Sim result. And here you see how you define these coefficients. Okay. Good. What we used also in our computational results later on, I mean, you don't have to solve these n+1 many problems. There are papers that improve on that so that you know that you can just solve a few of them and you get the robust optimal solution as well. So there is by Ivana and co-authors a paper, and then by Lee and Kwon in 2014, which is, as far as I know, the best result in terms of the smallest number of nominal problems that you have to solve. Good. So the question is, can we move this result also to bilevel optimization where you have a gamma robust follower? So the idea is, or the question was, is there a result stating that if you have this bilevel problem with a gamma robust follower, can you solve a finite number of bilevel problems of the nominal type so that if you take the maximum of those results, you get the solution of the original problem? We have a positive result for the so-called min-max bilevel problem. What is that? Min-max means that you have the same objective function for the follower variables in the leader and in the follower problem, only that you minimize here and maximize there. So this is why we call this min-max. Okay. It's a special case of the general bilevel problem where this f here is any vector, not necessarily the one that is in front of y here in the upper level problem. Okay. So we did this already before, and I mean, it's what you always do. You apply the stuff that you know, you extend it, you generalize it. So there was a tailored branch and cut method that we published for this kind of problem. But this was before we asked ourselves, okay, cannot we have a result that is similar to this Bertsimas-Sim result? So can we replace the robust bilevel problem by a finite series of bilevel problems of the nominal type? Okay. So back to this idea. Here's the problem again, f and f. So it's this min-max version of the mixed integer linear bilevel problem. And in this setting, if you have the optimal value function here, this is the reformulation, the single level reformulation of the nominal problem. In this case, it very much looks like Bender. So you really project out all the y variables, which is possible only in this min-max setting here. Well, and then what we know is that the value of this problem, which is the minimum of this one, if we replace the nominal optimal value function with the gamma robust one, that we can replace this here. This is the classic Bartzima-Sim result with the maximum over a finite number of lower level problems. But this does not help because you have it inside of your bilevel problem. You do not really know what to do with it. You have kind of a multi-follower setup, but it's not so easy to exploit this in an algorithmic way. You really want to move out the max over the finite set. You want to move it out so that it stands in front of everything. And the nice thing is that it works. So here's our main theorem, which is the positive result. So if you have solutions, we call them XL, which is a solution of the bilevel min-max problem of the nominal type, where you modify in the Bartzima-Sim way the lower level gamma robust objective function. And if you then solve all these L many problems and you take the maximum of them, then this actually solves the bilevel problem that you stated at the very beginning. So it's like the generalization of the Bartzima-Sim result to the bilevel setting, and it works. So what we did is we kind of changed the min-max-max structure to a max-min-max structure, where this max is just a finite max over, I don't know, n+1 many nominal min-max problems. So is it of any, so first of all, I mean, we had this result, we were of course happy, and then we said like, okay, what did Bartzimas and Sim did? Well, they exploited this and they extended it to approximation methods. So the result is there. If you have an approximation algorithm, you also get it for the nominal one. You get the same kind of result also for the bilevel setup. It just carries over. Okay, this is really a lower hanging fruit then. But the question, of course, is, does this help in practice? So how did we test this? We tested it with a knapsack interdiction problem. So you have a bilevel knapsack problem. Everybody solves a knapsack problem, but the knapsack here for the leader should be understood in a way so that all the items that the leader picks, they cannot be used anymore by the follower. And if the follower wants to maximize the value of his or her backpack, the intention of the leader is to minimize it. So it's kind of attacker-defender interdiction kind of setup. So we used the standard instances from the literature, and we deviated then, of course, the coefficients here of the objective function so that it fits to our setup. Okay, we varied a bit the size of the uncertainty sets. We varied a bit the gamma that we studied. So in total, we had something like 500 something instances. So, and we tested three things. So first, we implemented this branch and cut approach that we published first. I mean, this will be the clear loser. The good thing is this is published now, so I can be honest here. So this has no chance anymore, okay? So then the other one is we just use this min-max-max to max-min-max theorem that I just showed you. And we use, for the nominal problem, a general purpose solver, which is this interdiction cut-based branch and cut code of Fischetti and co-authors. And then we used another solver, and this is kind of one of the main features of this theorem. Whenever there is a tailored nominal new solver for your favorite problem, you can just use it in order to solve the robust counterpart of the problem. Okay, so there was by Weniger and Fukasawa this wonderful and extremely powerful new solver for bilevel knapsack interdiction problems, which is a kind of a breakthrough in terms of computational capabilities. So we used this as well. And here, I mean, if you just take a look at kind of parallel runtimes here, forget about idealized, think about parallel runtimes, you see that our former method takes in the mean, or let's say here in the median, something like 27 or 4 seconds. If we use our theorem in a general purpose solver, we significantly reduce this. If we use the best solver out there, which just appeared for our knapsack problem and that we can use only because we have this theorem now, it's just solved. Okay, so it is a huge difference in terms of computational capabilities. So here you see, let me go to the parallel runtimes again, a performance or a performance profile, and you see that if you solve the problem with this new and tailored solver that you can only use because you have this theorem, you outperform the standard approaches for these problems by far. So it really is extremely helpful in practice. Okay, so let me conclude. There were 2 parts. The first part was there are very many relations and even equivalences in some sense between robust and bi-level optimizations. I think these communities should talk much more with each other to transfer theory, to transfer algorithms and to exchange ideas. And the second thing is we showed that if we kind of combine robust and bi-level optimization, we can even generalize robust results to bi-level robust settings, which is nice and extremely helpful for computations. However, there's also an open point here. The question is, can I do this as well, proving such a theorem for the general case, which is not the min-max bi-level problem, but the general bi-level problem? We have some not so strong results in our preprint. We are not able to do that. We don't think that it's possible, but we don't have kind of an impossibility proof. So the general case and transferring the Bert-Siemers Zim result to the general bi-level setting is something that is still open. So if you want to work on that and if you have a result, please let me know. And with this, I'm done. Thanks.